Hello, I am Evan de Guzman from the pairing of de Guzman and Go, and this is our machine project 2 for LaviArc. So I want to mention the specifications that we received. The specifications that we receive are of the dot product. Now, essentially, we can represent a dot product as the summation of elements of vector A multiplied with corresponding elements of vector B. Now let's move on to the files that we have and that we would like to present. Firstly, we have the ASM file, and then we have the C file, and we have our round.batch file, which will be important later for compilation. But first, let's discuss the C file. Now, we have the two standard libraries for programming with C, and added to that, we have the time.h library. Time.h library will be useful later for uh, analysis and experimentation with the running time of these functions. Next, we have the external function prototype for the dot product of done in assembly, which we will also show later. Then over here, we have the dot product that is done specifically in C. As I said, that the specifications is the dot product and that we can represent it as essentially a for loop programmatically. And this would essentially mean that we are adding into a certain result the product between corresponding elements of A and B. Moving on to main, main would have the initialization of values and the passing of values into function. So firstly, we have this constant size t of n. Now this would mean that our variable n is a constant size all throughout the code. And the size t essentially makes sure that the c and NASM idea behind the number n is the same, considering that this would represent it as a 64-bit, considering we are a 64-bit computer, and NASM is a 64-bit assembly compiler. Next, this would mean that we have a certain value that is raised until 20, and this would be essentially 2 raised to 20. So that is our vector element size. And then next we have the declaration of our vectors A and B. As per requirement, the vectors must also be in a double data type. Therefore, we declare it as a double. And this is the most important part of the declaration, is that we allocate memory. As per suggestion and encouragement from our professor, it is best that we allocate memory so that we will be able to actually fit memory and pass it, considering that we are working with sensitive registers in assembly, and assembly doesn't really get to know uh, like what is a double data type as the same way in C. And then for this part, this is essentially our declaration of values in our vectors. There was a possibility to use randomized elements, but considering that uh, that's not easily checked for correctness, it is best that we could just use the large amount of values starting from 1 up until 2 raised to 20. And then on the other one, on the other vector, we have 2 raised to 20 up until 1. This would mean that it would always be a constant result, and it should always be a constant result. Now over here, we have the start and declaration of our clock. And over here means that whatever the result of the C and of the ASM, it will also be noted as a double data type. Now we start with the kernels, and we use first the C kernel. So line by line, this would mean that we are starting the clock. And then next, we are going to be assigning into result underscore C the result of this function for the dot product. And then we will end our clock, and we will put that value over here in also double time underscore C. And this would essentially give us the time it took to run this entire function. The next, we have the ASM kernel. In the ASM kernel, same thing, we start the clock, and then we pass our values into our external function prototype, and then we end the clock. At this point, it is best to move on to SASM so that we could show the code. This is very standard, so as to uh, declare that, oh, this is that we are going to be working with an external function. And then next we have exarps xmmo. This the same thing as sorax, but only for floating point values. And then next we have essentially a local function into the dot product, which is called loop, and compare rcx 0. So when it comes to passing values from C into NASM, for integer values, whole number values, they would always go first into RCX. So this would mean that, oh, we are given an RCX, and that we could use it as our looping counter. And if RCX is 0, we jump to done. But let's move on. This is essentially saying that we are moving into XMM1 the first value, and then also this we are moving into XMM2 the next value that we received, and then we will do the floating point multiplication of XMM1 and XMM2, and we will add the result of this, which will go to XMM1 into XMM0. XMM0 is what is used for SIMD registers to be displayed into C in the same manner as it is racks for integer values. Then this would essentially mean that we will move on to the next, and that we will decrement our counter up until it reaches 0. And should it not be 0, obviously, we will jump back to the start of loop. Now, since we are finished with that, let's run the batch file. So the batch file is essentially all the compilation and connecting codes, so that we don't have to type it over and over again. So we will get our object files, and then we will get our .exe file. So to run the .exe file, we just type in cmd then mp2 underscore c file.exe. Then we are given this. I can't really show the correctness of this by hand, considering it is a very large value. But the dot product in C is the same as the dot product in assembly, and thus we can check it to be both correctly implemented.